Üniversitemizin 250. yıl etkinlikleri kapsamında düzenlediğimiz teknoloji seminerleri etkini bu dönem Sayın Doktor Can Gülen'in gerçekleştireceğiz. Kendisinin katılımıyla onur duyuyoruz. Hoş geldiniz. Doktor Can Gülen 1985 yılında Boğaziçi Üniversitesi'nden alanından mezun oldu. Daha sonra yüksek lisans derecesini Syracuse Üniversitesi'nden aldı. Aynı zamanda MBA derecesi aldı. 1992 yılında da makine mühendisliği alanında doktora unvanı kazandı. Sonrasında yaklaşık 30 yıllık sanırım endüstri deneyimi var. Büyük bir kısmı Amerika'da tanınmış firmalarda gerçekleşmiş. Thermoflow'da çalıştıktan sonra General Electric önemli bir kariyer gerçekleştirdikten sonra şu anda Bechtel'de Infrastructure and Power Corporation'da Senior Engineer baş mühendis olarak çalışmakta. Kendisi bize karbon yakalama başlıklı bir seminer verecek. Bize fosil yakıt bazlı enerji santrallerinden karbon uzaklaştırmak için mevcut teknolojiler, geçmiş durumdan ve beklentiler hakkında genel olacak. Kendisine katılım için tekrar çok teşekkür ediyorum. Seyhan Hocam, siz de bir şeyler söylemek
için öncelikle söz almak istedim. Öncelikle Mesut Hocamıza çok teşekkür ediyorum. Dekanlığımıza bu semineri olanağını sağladığı için. Şimdi özellikle enerjiyle ilgili çalışan arkadaşlarımız hidrojen, karbon capture gibi konularda çok büyük bir bilgi kirliliği içerisinde olduklarını hissediyorlardı. Bunlar önemli konular fakat bir mühendisin herhangi bir konu ya da herhangi bir problemin çözümünü incelediğinde tüm yönleriyle ele alması ve sayılarla ele alması ve uzun dönemli tahminler yapması, uzun dönemli öngörülerle o mühendislik sistemine gereken önemi vermesi gerekiyor. Bu açıdan Gülen hocamızın kendisi benimle olan yazışmalarında ben hoca değilim der ama bence hocalık insanlara örnek olmaktır. Kendisinden özellikle geçen yıl 21 Eylül'de yaptığı hidrojenle ilgili sunumda muhakkak izlemişsinizdir. Fiziksel olarak olması bile uzaktan çok ufuk açıcı, moda deyimle ufuk açıcı bir sunum yapmıştı ve çok yararlanmıştı. Ve o sunumdan dolayı birçok arkadaşımız konuya daha farklı bakıp daha farklı kaynaklar, daha farklı bakış açısıyla bilgisayar çalışmalarını sürdürmeye başladılar. Ben bir yıl içerisinde buna tanık oldum. Buna ben de dahilim. Bu yılda karbon capture gibi son yıllarda çok gündemde olan konuda bize gerçekten sayılarla bilimsel olarak mühendisçe bir sunum yapmayı kabul ettiği için kendisine gerçekten kendi adıma ve hepimizin adına çok teşekkür ediyorum. Çok sağ olun.
Mikrofon var. Okey. Teşekkürler. Nasıl, iyi duyuluyor mu? Mikrofon çalışıyor mu? Okay. Well, rahmetli Cem Karaca'nın deyimiyle merhaba gençler ve daima genç kalanlar. Sunum maalesef İngilizce olacak. Maalesef dememem lazım. Teknolojide İngilizce günümüzde lingua franca. Ama bunun sebebi yani kimseye hava atmak değil. Benim kariyerimin tamamı Amerika'da geçti. Benim İngilizce, bütün dokümanlarım, bütün bilgilerim İngilizce. Şimdi onları tercih etmeye kalkarsam ortalık duman olur. O yüzden ama anlayamadığınız yerler falan varsa yani durdurun yani. Anlamaya çalışırım. 30 tane slide var. Biraz detaya gireceğim. Seyhan Hoca'nın dediği gibi Eğer bir şeyi hesaplamayı bilmiyorsunuz kısa yoldan kağıt kalemle, o konuyu bilmiyorsunuz demektir. Size her şeyi yuttururlar. Okay? Bu konuşmalar, bu sunumdan hiçbir şey almıyorsanız bunu alın. Ya, not tutmaya falan kalkmayın çünkü galiba dağıtılacak değil mi şey, yani available olacak herkese ya, PDF.
Eğer sizin
Veriyor. PDF'e bakarsınız, şey yaparsınız. Bazı slaytlarda kenarda bazı referanslar veriyorum. Herkesin o referansları edinmesini kuvvetle salık veririm. Türkiye'nin ekonomik durumu malum ama bazıları yani gerçekten çok para tutmayan şeyler ya da üniversitenin kütüphanesinden bulabilirsiniz. Onları edinin, en azından bakın. Benim burada anlattıklarımın daha detaylı background'ını orada bulabilirsiniz. Dediğim gibi yani bu konuya merakınız varsa ıvır zıvır şeyleri okumayı bırakın. Okay? Rakamlarla açıklanmayan, desteklenmeyen hiçbir şeye inanmayın. Kendiniz hesaplayın. Dediğim gibi eğer bir konuya gerçekten vakıfsanız Excel'e bile ihtiyacınız yok. Microsoft Excel'e bile. Kağıt kalem yeter. Bir de herkesin telefonunda bulunan kompüter deyip let's start the show. Okay, CCUS, we're talking about the carbon capture today. The terminology, the acronym that is widely used is the CCUS. It means carbon capture, usage, and storage. Carbon here is, of course, is a shorthand for carbon dioxide. The capture that we're talking about is basically getting rid of the carbon dioxide in the flue gases from the fossil fuel power stations and industrial facilities like cement factories. That's the capture. It requires a lot of megawatts, requires a lot of energy, power, and it's very expensive. So that's the main impediment in doing that at a wide scale. As I will show you in the following slides, carbon capture is being done very widely, especially in the United States. There are many facilities, but they are at a different scale. And magnitude, everything, than what we are trying to do here in order to make a meaningful impact on carbon dioxide emissions from power plants and industrial facilities into the atmosphere. Of course, capturing it is not enough. You have to do something with it, and there are two possibilities for that. You either store it in underground geological formations, or use it. And use can be by conversion or non-conversion. Non-conversion is the widely utilized and known means for that is enhanced oil recovery, which means injection of carbon dioxide into the deep oil fields where the recovery became very difficult, so that you squeeze the oil upwards and make use more of the potential of the existing reservoir. Global usage of carbon dioxide is an industrial gas widely used to the tune of 230 million tons per year globally. 130 million tons is used in urea manufacturing, which of course is turned into fertilizer. And 70 to 80 million tons is used for enhanced oil recovery, as I described. And by far, the most of that, to the tune of 50 million ton, is in North America, United States and Canada. And then when you convert it industrial CO2, you make a lot of stuff that you see here. Now this book, it's available on Amazon, written by Howard Herzog. He's a well-known authority in the field. It is cheap, about 16 bucks. Okay, and I noticed also there is a Turkish translation of that available. So whichever you prefer, buy it, read it. You can read it in one night, okay, and keep it under your hand if you are interested in this field, and then it's going to explain you many things. Okay, so CCUS, so why? What is the reason? Well, the reason is, as it's shown in the upper graph, there is a very strong correlation between the CO2 emissions to the atmosphere, especially anthropogenic emissions, meaning human-caused emissions, and increase in the global average temperature. Okay, so that's the reason. In order to put a brake on that increase in temperature, which is leading to climate change and catastrophes associated with that, there is a need to stop and even reduce carbon dioxide in the atmosphere. The graph on the left shows the numbers. It's interesting to see that there was a dip here during the pandemic, which shows that how much the industrial activity on Earth is causing carbon dioxide emissions to the atmosphere, and it picked up readily, and we are on the same path. And what is intended to do is to reduce that. And can it be done? Well, at the end of the presentation, you will, I hope, get an inkling of whether this is possible or not. I am going to, by virtue of my business, I'm going to focus on the power sector, emissions from the power sector, but power sector, electric power generation, is neither the sole culprit in CO2 emissions, but it is not the largest one. It's the largest one, but not the sole. There are other sources. As far as, this relationship between the CO2 in the atmosphere and the temperature rise, there are two sides of the coin. So I strongly encourage you to look at both. Okay, do not believe the zealots, ignore the right-wing nutcases who are trying to peddle conspiracy theories about the climate change and etc. But this is not a settled thing like the ideal gas equation of state. Okay. You know the pressure and temperature, and you could calculate the volume of the gas. The calculations that are leading to these conclusions are not that deterministic and concrete and proven. I highly recommend to look at that book by Stephen Koonin. He's a physicist, and he was a science advisor to the Department of Energy during Obama administration. He has something to say about these strong conclusions. And as far as the sustainable energy, this book on the lower right by David McKay, he passed away several years ago. It's by far the best resource to read and understand, and it's available on the web as a free PDF. Okay, download it and read it. Okay, technology space, as far as the carbon capture, you have a feedstock. It's a hydrocarbon fuel. You burn it and you make something with it. And then the gases that result from that combustion contain carbon dioxide. In order to mitigate that carbon dioxide that's associated with that process, you have several possibilities. I'm only talking about here or showing here only the most important ones. Post-combustion carbon capture, which means capturing the CO2 from the flue gas, stacked gas of power plants. Pre-combustion is basically you take a feedstock like coal, you gasify it, you make a syngas, and that syngas after a water-gas shift reaction contains CO2. It's at higher pressure and higher concentration, so therefore it's easier and less expensive to capture. So that's one way. The other way, and there is also a technology which is recently promoted, which is called oxy-fuel combustion. Oxy-fuel combustion, basically instead of air, you are using oxygen, which of course must be produced first, and therefore again, it's an expensive process. But if you do that, the exhaust gas contains only CO2 and H2O, water vapor. As I will show later, if that can be done in a closed loop system, you you can easily capture CO2 by condensing the water out in a water-cooled condenser. So, and then there is chemical looping, which is right now, it's, you can read about it. In these references that I list here, the synthetic fuels, again, it's available on Amazon. It's a Dover's soft cover edition, so it's not very expensive, maybe 20 bucks. Again, I mean, I know. But if you can, buy it, okay? It's the Bible of synthetic fuels. Yeah, chemical looping is basically science fiction right now. So technology readiness level of the technologies in the carbon capture value chain. You can see many of those. Only the green highlighted ones are today being utilized at a commercial scale. And I'm going to focus on those in this. Obviously, even in a cursory presentation, it's almost impossible to go through all of them. I will talk a little bit about, the chemical absorption technology to capture the CO2 from the flue gas. This one, hydrogen from gas with carbon capture, okay, which is the pre-combustion. And then I will talk about a little bit about, where is that? Enhanced oil recovery, because it's the mostly used technology to make something with captured CO2 at commercial scale. Okay, some numbers. Again, in order to be able to talk about the subject, you have to be conversant in the numbers. First of all, today, an atmospheric CO2 concentration is measured rigorously since late 1950s in an observatory in Hawaii. And today, the number is for about 420 parts per million by volume, which corresponds to 0.04% by volume in air. By weight, it's about 640 parts per million. Total mass of atmospheric air is about 5 million gigatons, okay? And therefore, you can calculate that there is about 3,300 gigatons of CO2 in the atmosphere. So this is the number that we're talking about that's causing us problems for global warming. Now, as I said, so one way to mitigate CO2 emissions is to eliminate or to capture the CO2 in the flue gases from thermic power plants. And there are two types of plants today, coal-fired plants and natural gas-fired plants. So if you know the heat rate of the power plant, which is the efficiency, and the lower heating value of the fuel that you're talking about, you can easily calculate the carbon dioxide footprint of the exhaust gas of that system. The formulas are very simple. You can find them in the chapter which I had written in that handbook. But I mean, they are simple. You can just copy this and do the calculations, as I said, on a pen and paper, with pen and paper. So obviously, today's state of the art in natural gas-fired electric power generation is gas turbine combined cycle. 60% net LHV is a good yardstick to use. Its carbon footprint is about 330 kilograms of carbon emissions for each megawatt hour generated. If you are talking about a supercritical pulverized coal power plant at 40% efficiency, which is not bad, you're talking about 800 kilograms per megawatt hour of generation. And if you are using a dirty, problematic fuel like lignite, then you are talking about more than 1 metric ton of CO2 per megawatt hour generated. This graph shows the situation, carbon footprint as a function of plant efficiency. And you can see that, I mean, without even concentrating on the numbers themselves, today, I mean, ideally speaking, there is no chance for coal-fired power generation to be a feasible technology. Okay, it's carbon footprint of even the most efficient coal-fired power plant that you can find is much worse, which means much higher than the lousiest natural gas-fired power generation system. Okay, but as you know, the reality of life is such that coal is still being used very heavily in many parts of the world. In the United States, it's on the wane, okay? But the reason for that was not the kindness of the hearts of the people in the energy industry. I mean, it was just bare economics, because with all the environmental regulations imposed on coal-fired power plants to scrub the stacked gases, the price of a coal-fired power plant is much, much higher than a natural gas-fired combined cycle. So they are being phased out and not being built anymore, and therefore today natural gas power generation in the United States actually surpassed coal-fired generation. Now some more numbers. Again, the numbers that I'm more familiar are, of course, United States, but I mean you can I mean expand or extend or extrapolate to other situations in the world. I mean the answers are not going to change much. From all the power plants in the United States, about 0.95 gigaton of CO2 emissions come from coal-fired generation, and about 0.56 gigaton comes from natural gas-fired power generation, which is of course commensurate with what I have shown earlier. So a total of 1.5 million metric tons. And if you do the math again, which is very simple shown here, it corresponds to about 0.2 parts per million by volume. So here is the reality that we are facing, okay? I mean, forget about all the hoopla that you read. Today, the average in the atmosphere is 420 parts per million by volume. If I stop all the thermic power plants in the United States tomorrow, okay, shut down, gone. This is the impact, 0.2. And I can guarantee you all the cows farting in India are going to negate that. So, okay, I will leave it at that. Enhanced oil recovery, as I said, okay, you capture the CO2, okay, what are you going to do with it? You have to either store it, find a place to stick it in the ground, or do something with it. You can produce only so much fertilizers, you can only produce so much Coca-Cola and Pepsi-Cola, okay? So this is the most widely used industrial way to make use of captured CO2 and it also makes a lot of economic sense because oil producers are willing to pay for it. They need it to get the oil from under the ground where it's difficult to get out otherwise. Today, the 2010 number in the United States is about 9 million metric tons of CO2 used for enhanced oil recovery. And where is it coming from? Well, actually, believe it or not, there are natural CO2 reservoirs in the country, okay, where CO2 is residing underground. So that's one thing, actually, that should soothe the nerves of those people who say, oh, if you capture the CO2 and store it underground, what if it escapes, okay? It's not that easy to escape, all right? So it's not going to happen like it happened in one place in Africa some time ago. There was a big carbon dioxide release from underneath a lake. That big bubble came out and killed everybody around the lake. Something like that is not going to happen if you do it right. And there are examples which are naturally occurring, and that CO2 is the source of enhanced oil recovery. The other is from other sources. I will talk about a little bit later, but carbon captured from other industrial processes. But again, let's look at the numbers. Let's say it's 10 million metric tons, okay, CO2 needed for EOR in the United States or in today. So let's say that we increase it tenfold, okay? It's impossible to do in any meaningful amount of time. So it's 100 million metric tons. And well, I just showed you that the amount of CO2 that we have to get rid of is 1.5 million metric tons. Okay, I mean, do you see the magnitude of the problem? We have to find other uses and holes in the ground to stick the CO2 into it in order to make some meaningful difference. And even if it could be done, as I had shown earlier, it's barely a drop in the proverbial bucket. So let's look at the thermodynamics. So capture, let's say this capture is a mysterious process. We don't know what's going on, so therefore we can simplify it. Let's call it a black box, okay? Whatever is happening in it, the bottom line is you have a feed stream, and that stream is the exhaust gas from a power plant, okay, containing CO2, and the red font text underneath that feed stream shows the amount of CO2 in different sources. And then that capture process creates two streams out of that single feed stream. One is the product stream, which is the CO2-free gas. And the other one is the product stream, another product stream, which is basically the CO2 with very high purity. So then the question becomes, as I had said in the beginning, you're talking about a process requiring many, many megawatts. So how much? Okay? I didn't show you here a flow sheet model of a carbon capture process. I mean, you couldn't even see anything meaningful. It is so complex, complicated, busy. But let's start from the basic principles. Well, the work, minimum work needed to accomplish this is given by the second law of thermodynamics. It's the net work potential, which is the exergy of the product and the feed streams. And I will leave it at that because otherwise we are going to run out of the time, but you can show this. This is a book that I had written and published recently, Second Law Analysis. There you can find it in a way that's more applicable to practical processes, but I mean any thermodynamic book that you used in your introductory thermodynamic class, even if you have a copy of old Venerable Van Wylen and Sontag, okay? You can find it there, but hear me now, believe me later. This is it. So it can also be shown that this exergy quantity, which comes from the second law of thermodynamics, if you are talking about a constant pressure and constant temperature process, is equal to the change in Gibbs free energy. And for the process that I have shown earlier, simplified process, at constant pressure and temperature, you can very easily calculate that number if you know the compositions of the streams, feed stream and the product streams. All right? And the underlying theory is explained in this book by Jennifer Wilcox. Again, I highly recommend it to those people who are serious in carbon capture. It's very, very illuminating in bringing up and explaining the theory of the carbon capture. So, but at the end of the day, the formula that you have to use is just this, believe it or not. And if you do that with different types of gas feed streams, you will see the behavior shown here on this graph. And it's simple to understand even without any math. Atmospheric air contains, as I mentioned, 420 ppm per ppm by volume CO2, which is 0.04%, okay, by molar concentration. The minimum separation work is about 134 kilowatt hour per ton of CO2 capture. If you talk about a coal-fired power plant, where the amount of CO2 in the flue gas is to the point, it's about 16% by volume, orders of magnitude higher, and the minimum work is only 39, much lower, right? And you can think about it this way. You have this, let's say a box, and there are let's say bigger box, okay? Let's say there are 100,000 white balls in it. Now, which one is easier? To find the 4 black balls in that thing, or to find like 1,560 or whatever balls in that, okay? Which one is easier? Of course, the other one, right? The same principle also happens when you try to pick the CO2 molecules out of that gas. The higher the concentration of the CO2 in the feed stream, the easier it is to do. And the numbers do not seem too horrible, right? I mean, you know, why are we not doing it? Because these are the ideal numbers. Actual separation work is much, much higher. This is the data of different processes where this capture is done. The concentration ratio is the ratio of the final concentration of the CO2, which is in the product stream, and it's higher than 99%. And then the initial, which is 0.04 for air, 16 for coal-fired power plant exhaust gas, and about 4 for natural gas-fired plant. So that concentration ratio goes up. The second law of efficiency, which is the ratio of the minimum work to the actual work, goes down. Okay? So if you apply it to the minimum works that were calculated in the previous slide, and this is a curve fit in a paper by Wilcox. You can find it in her book also, but this is from the paper cited here. And if you use the efficiencies, these are the numbers that you end up with. For example, if you want to remove CO2 from the atmospheric air, which is called, by the way, direct air capture, which I'm going to discuss in the final slides, the actual work can be as high as 2,500 kilowatt hours per ton of CO2. Okay, it's a crazy idea, basically. But even the easier cases, I mean, these are big numbers. For example, for the combined cycle, it's about 400 kilowatt hour per captured ton of CO2, and which is a big number, we will see. But these two slides give you everything to calculate, to make a reasonable estimate of what is involved in carbon capture, okay, in terms of energy, power requirement. The technology, the most widely technology used is chemical absorption, and it's not a new technology. It was invented in 1930 by Mr. Bottoms in the United States, and he obtained a patent for it. The picture that you see on the left is from his patent, and believe it or not, today, 80 years later, this is still the process that is being used to remove CO2 from gases or any other stuff. For example, in the chemical process industry, it is the, maybe it can barely become feasible, but there is a caveat, as we will see later. This is a typical advanced class gas turbine combined cycle, about 600 megawatts, 586 to be exact, 63% net LHV efficiency with an advanced gas turbine. Its carbon dioxide footprint is 314 kilogram per megawatt hour CO2, and for 90% capture to be applied to this power station using the methodology that was shown in the previous slides, you are looking at 65 megawatts of power to be spent, which has to be subtracted from that 586. That doesn't include the compression of the CO2, which has been captured, okay? Because as we have shown earlier, when you capture the CO2, you have to do something with it. In order to do something with it, you have to transport it to some place through a pipeline. In order to be able to do that, you have to compress the CO2. The final pressure of the CO2 depends on the use, okay? If it's enhanced oil recovery, which is 1,000 miles away from your power plant, you may need more than what is shown here as an end pressure, which is 125. So the range can be anywhere between 125 bar to 155 bar. And the CO2 gas pressure at the end of that regeneration process is slightly higher than 1.1 bar, 1.25 bar. So it's a stupendous amount of CO2 compression that you have to add to that 65 megawatt, which is just the capture work. And so that the total comes to 82 megawatts. Your 586 megawatt power plant becomes a 500 megawatt power plant, 14% loss, which was actually the number shown in that slide. And from 63% net efficiency, you come down to about 54%. And the capture work is about 500 kilowatt hour per ton of CO2. So these are realistic calculations, but I mean, if you really look at a power plant, depending on the site conditions and all the other stuff, I mean, you may end up with much higher than that. So it's on a case-by-case basis. And there are, so here This is the type of number that you have to figure for compression, about 100 kilowatt hour per ton of captured CO2. There are two types of compressors that you can use, and you can read about that in that handbook in the lower right corner. Again, it's a book that I highly recommend. If you can find it, get it, or if you can find it in your library, school library, take a look at it. Two types of process compressors that can do that, inline or integrally geared. This is not a simple compression process that you can see from that integrally geared compressor configuration, because in order to get the best performance across such a high pressure compression ratio, you have to divide the compressor into different sections and that have to rotate at different speeds, which is done by that gear arrangement. Today it is considered a mature technology, okay, but there are still some bugs associated with that, and it's difficult to find about these problems. But the scuttlebutt that we heard about the Petranova capture demonstration was they had some problems with those integrally geared compressors there. So inline compressors, they are going to be less efficient, therefore they are going to consume more power, but they are going to be more reliable. And in a power plant, whatever it is, reliability is the most important consideration than efficiency. This is interesting. So CO2, if you compress it, evet. O ikisini birleştiren yani vallahi şimdi şurada göstereceğim de yani refrigeration var ama başka bir sebepten dolayı bu beni şaşırttınız şimdi. I have to go back to English. So that's a huge compression to 120 or up to 150 bars. The critical pressure of the CO2 is about 83 bar, I believe. So you are going to the supercritical pressures. In order to reduce that compression power, they are looking at some gymnastics. So there are different stages. Stage 1, compression, intercooling, compression, intercooling, compression, intercooling. You come up to here, and then you cool it, and then you bring it to this region. And instead of a compressor, the last stage is a pump. Consumes less power. Or you go even crazier. You go not to the 6 or 7 stages, but only 4 stages, and then you go and cool the carbon dioxide cryogenically. You end up at this very low temperature, and then you pump it. Okay, but those are ideas. I don't think they are going to be very difficult to implement anytime soon. Very complicated. Yeah, about 30.
Liquefaction yerine doğrudan doğruya gaz olarak soğutma çevriminde kullanmaları mümkün ama basınç nedir? Basınç aralığı yakaladığı zaman o toprak altında.
Toprak altında 150 bar falan filan, depending on the application. So this is the performance hit breakdown. So we calculated it, 82 megawatt including the CO2 compression. So 29 megawatt of it, first of all, from the lost steam turbine power output, because you have to extract the steam, which is going to be the heat source for that reboiler in the regenerator. Okay, and that one is a large amount, because this is the amount of heat that you need to do that regeneration. It's 162 megawatt thermal, which comes from low pressure steam extracted from the steam turbine, and you end up with a reduction of 49 megawatt of output. So those are the things that come into consideration. Again, this stuff can also be, you can easily calculate because you know the flue gas, okay? You know the flue gas composition. With that, you can calculate the CO2 coming out with the flue gas. When you say 90% capture, you find the amount of captured CO2. And with the standard amines, you need about 3,500 kilojoule of heat energy to do that. And with that, you can easily calculate how much heat you need. And if you know that, you can find how much power hit is going to result in the steam turbine. So all these calculations are easy to do for all types of power plants, and they give you a flavor of what is involved in real carbon capture. There are many projects. This I took from a 2014 paper. You can see that pretty much all of them have been canceled. Why? Because of that. It's very difficult to do. It doesn't become economic, costs a lot. They start, they come to a point and they say, screw it, we're giving up. You see, so many. Out of those, there are only 4 that the one in China, I couldn't find any real information. It may or may not have been canceled yet. Those 2, Petranova and Boundary Dam, those 2 major pilot demo plants have been in operation. Petranova had closed in 2020, but it's reopened again. Boundary Dam was using a proprietary solvent developed by Shell called CanSolve to do the capture, not a generic amine. And Petranova was using a solvent developed by Mitsubishi Corporation. Japanese were behind it, and what I heard is it was closed because it didn't do what it promised to do. But Japanese didn't give up on their technology. They bought the power plant, okay, the system, and they restarted it. Camper is a notorious example. It has been completed, but and to the tune of $7.1 billion, okay, more than 12,000 per kilowatt. It was an integrated gasification combined cycle plant with pre-combustion CO2 capture. Unfortunately, they were never able to make the gasification and capture part to operate, and it was canceled. Now only the combined cycle part is running with natural gas. You can read about it. It's going to give you a good flavor of difficulties involved in carbon capture. As I said, carbon capture is done presently in many industrial facilities in the United States, and probably someplace else too, but these are only the large projects with more than 800,000 tons per year of CO2 capture, and the captured CO2 is used for different purposes shown there. But it goes back 40, 50 years. It's a mature technology. But these are different processes, chemical processes and etc., where the carbon dioxide content in the gas, which is being scrubbed, is high. 30% maybe, can be more, and at very high pressures. So therefore, the process is easier, and the system is cheaper, and that's how it's done. It does not mean that you can do it in a chemical facility, that you can translate it easily to a power plant. That's a big difficulty. Transport, of course, costs some money. So if you have a power plant in the middle of nowhere, and if you make the CO2, of course, I mean, you have to, unless you are standing next to the place of use, you have to transport it. There are 2 ways to do it. And by far the common one is the pipeline. And this is how much the pipeline transportation costs, shown in the lower left graph. And there is about, I believe, 6,000 miles of CO2 pipeline in the United States at the present. And the main use is basically take the CO2 from those facilities. And there are many more facilities like that, but with much, much lower amount of capture. So CO2 captured here is basically transported all over the place in North America through that pipeline network. They are looking at ship transport, but it's very expensive. It's on a case-by-case basis. You take a 50-50 by weight feedstock of Powder River Basin coal, which is a sub-bituminous coal, and a biomass, which is corn stover. Corn stover is what is left in the field after you harvest corn. So that's and it's a biomass, therefore it's carbon neutral, which means that you say, oh, that corn stalk that was grown by the photosynthesis process, taking CO2 from the atmosphere. So therefore the CO2 generated by burning it doesn't count because you took it out, now you're putting it back, carbon neutral. So that's why it is in the feedstock. So you take that feedstock, you put it through a gasifier, you make a syngas, and then that syngas contains carbon monoxide and hydrogen. Those are the two biggest components in that gas. Then you put it through a water gas shift reactor. You convert that CO to CO2 so that the gas has high CO2. The pressure is around 335 bars, very much higher pressure than the post-combustion capture, which is happening at pretty much atmospheric pressure. And then you can capture that CO2 along with hydrogen sulfide in a pre-combustion capture process similar to what I have shown earlier. And then you make sulfur from the captured H2S, and the captured CO2 is sent to the final place of usage. And the gas that is coming out of that carbon capture process has very high hydrogen content. And you put that through a pressure swing adsorption process, and you make pure CO2. And the remaining tail gas from that process is burned. That tail gas contains 30% by volume hydrogen. It is used in a gas turbine combined cycle power plant to generate about 134 megawatt power. 84 megawatt are consumed inside the power plant and also by the ASU, which is generating the O2 for the gasification. So it gives 50 megawatt to the grid. So nominal CO2 capture efficiency is 76% because we are not capturing all the CO2 in the gas. Why? Because biomass is carbon neutral. So capture is only slightly higher than CO2 attributed to the combustion of the coal, and therefore it's a net negative. It's beyond net zero. So it removes, strictly, arithmetically speaking, with the biomass arithmetic, it's a net negative CO2 process. It's a good idea. So it makes blue hydrogen. I don't know if you heard about it, but it's this gasification of a solid fuel stock and making hydrogen with carbon capture. That's called blue hydrogen. Because today hydrogen is an industrial gas, and by far most of it, 90%, is generated by steam methane reformation, which creates a lot of CO2. It's gray hydrogen. There are ideas to apply carbon capture to the SMR, steam methane reforming, but it's not a good idea in my opinion, because you can do the gas turbine combined cycle burning methane and do the post-combustion capture. It's easier and cheaper. So this one makes sense because at least in the United States, in North America today, and in UK, you cannot build a coal-fired power plant anymore. It's untouchable. So basically you have a reserve, energy reserve. You cannot use it because it's not clean and it produces CO2. So therefore, by this process, you take that untouchable and make something good, which is hydrogen. Okay, but whether it's going to be cost effective or not remains to be seen. All the technologies here are known technologies, but still it's an expensive system. Whether it's going to be cost effective or not, as I say, remains to be seen. Who knows? And then finally, CO2 removal. This is the direct air capture. How many people here heard of direct air capture? Yeah, it's a crazy process. So you are trying to scrub that 400 parts per million CO2 from the atmospheric air. It's the same general scheme as the CO2 capture process that I described. It's the removal of the CO2 from the feed stream. In this case, the feed stream is atmospheric air using a solvent, and then regeneration of that rich solvent. And there are two options there. Chemical, which is current state of the art, which is similar to, no, I take it back. It's much more convoluted than what I described for the amine-based process. Or there is a very neat process, electrochemical process. I know a lot about it, but I didn't include it in this presentation, so you can look it up. But it's a very neat idea. It's as difficult to do as the other, but might have a chance. The absorber, that's a column, is replaced by an air contactor, which is very similar to a cooling tower with fill. The stripper is replaced by a chemical process plant, quite complex, due to the low concentration of CO2 that you need to capture. It is very large. It requires complex equipment, and it's very costly in terms of capex and also energy. It's consuming about 1,500 kilowatt hour per captured ton of CO2, which, as I have shown, was only 500 for that post-combustion process for the gas turbine combined cycle. Today, the optimal capture rate is found to be around 75%. In order to capture 1 million tons per year of CO2 from the ambient air, you have to process 1.81 million meter cube of air. And in order to be able to do that in this air contactor, if it's 10 meter high, which is like a 3-story building, you need this to the tune of 4.6 kilometers. And if you make it 20 meter high, you need 2.3 kilometers of this to capture a meaningful amount of CO2 from the air, okay? Well, so, I mean, I leave it to, and then, as I mentioned, once you have that solution, which is CO2 rich, you have to go through a very complicated process, which requires a lot of heat and power. I mean, forget about it. That's why I said the electrochemical process is much more elegant, simpler, but also, of course, it also consumes power, and it's going to need that contactor also. And so let's do, if you do some math, so we saw the numbers, right? Average US coal-fired generation, 1,000 kilogram of CO2 emitted for each megawatt hour of generation. The number is 400 for average combined cycle natural gas-fired system. DAC, direct air capture consumption, is 1,500. So therefore, just look at the coal-fired one. 1 ton of CO2 emitted for each megawatt hour of generation, okay? But you capture only 0.7 ton of CO2 with direct air capture. So you have a deficit of 0.3. So you build a 4.3 kilometer long system at whatever cost, and all you do is, if there's a lot of CO2 generation by coal-fired generation in your area, your deficit, you're not even removing carbon dioxide from atmosphere. There is still deficit. Now, if it's a natural gas heavy thing, then your net removal is only 0.3 ton for each megawatt hour. So, okay. I don't know. If you are willing to buy the Tower of Galata, I can sell it to you if you believe that this is going to work. Oh yeah, of course. I mean, there's also this life cycle CO2 thing. Yeah. All right, this is the story of the carbon capture. Any questions?
Günün dünyasında biz enerjisiz yaşayamayız. Dolayısıyla termik santrallerin olması gerekir.
Tabii.
Ve biz ülke bazında yaklaşık 80 kusur yüzde olarak 80 kusur yüzdesini enerji ihtiyacımızı termik santrallerden elde ediyoruz.
Amerika
Geri
aşağı
kalanı
yukarı.
bilmem güneşten, rüzgardan, jeotermalden olabilir. Evet, şimdi bu ihtiyaç olmazsa olmazdır. Elektrik ihtiyacı, enerji ihtiyacı olmazsa olmazdır. Bu durumda termik santralin kurulması gene de olmazsa olmazlardandır. Bu durumda termik santralde ısıya ihtiyacımız var. Bu ısıyı biz Türk kömürleri, kötü kömürleri yakarak elde edebiliriz. Bir, doğal gaz yakarak da elde edebiliriz. İki. Tek fark, önemli fark. Türk kömürleri yereldir, bizim kendimizindir. Mal kendimizindir. Doğal gaz ithaldır. Ama kötü kömür atmosferi çok kötü etkiler. Çok kötü şekilde atmosferi kirletiyoruz ama doğal gaz çok az kirletecektir. Tek fark dediğim gibi Türk kömürleri kötü olsa bile yereldir, bizimdir. Doğal gaz ithaldır, Rusya'dan, bilmem İran'dan, Afrika'dan ithaldır. Siz bir yönetici olarak termik santral kurulması safhasında doğal gaz mı tercih edersiniz, Türk kömürü mü tercih edersiniz?
Vallahi onu buradan cevap veremem, yani onun incelenmesi lazım ama yani rezervi bir şekilde değerlendirmek lazım. Onu en temiz nasıl değerlendireceksiniz? Onu işte dediğim gibi mesela linyiti şu gösterdiğim şeyden geçirebilirsiniz. Hidrojen yapabilirsiniz mesela linyitle ama o zaman garanti ediyorum size ithal ettiğiniz doğal gazdan çok daha pahalıya mal olacak.
Tonu bakımından Amerika, Çin,
Evet.
Hindistan ve
Çin geçti galiba. Çin ya bilmiyorum, tabii endüstriyel ülkeler en tepede. Çin galiba herkesi geçiyor çünkü çok fazla coal-fired power plant yapıyorlar. Hindistan'da çok. Tabii bir de başka türlü salınımlar da var. Yani odun yakarak yemeklerini yapıyorlar, ısınıyorlar, bilmem ne yapıyorlar Hindistan'da. Onun da tabii çok büyük etkisi var yani. Ama tabii endüstriyel ülkeler en tepede. Yani. O çoktur canım, çok daha fazladır yani.
Siz yıllardır bu enerji işleriyle uğraşıyorsunuz. Bütün enerji türlerine baktığınızda hani yenilenebilir ya da değil. Birinci ve ikinci olarak hem gelecek vaat eden hem de yatırım. Benim imkanım olsa ben bu işlere yatırım yaparım dediğiniz şey nedir? 1 ve 2 numara. Enerji türü olarak.
Yani olması gerekeni biliyorum, yani olması gereken nükleer yani. Nükleere ağırlık verilmesi lazım. Yani wind, rüzgar ve güneş akıllı olarak yapılması lazım. Çünkü çok dispatchable değil yani. Yani kapasitesi düşük. O yüzden energy storage, enerji depolama sistemleri olmadan onu yaparsanız çok zor oluyor yani. İşte natural gas'i mümkün olduğu kadar yapmak, kömürün yerine kullanmak. Yani kömürü de carbon capture'la yani kullanacaksan kullanmak. Yani yatırım yapacaksan ne bileyim çok uzun vadede yani ben olsam nükleere yatırım yaparım yani bir şekilde geri gelecek. Ama yani benim ömrüm yetmez. Belki sizinki yeter yani. Yani Amerika'da falan filan kömüre yatırım yapmam yani mesela. O bitti, öldürdüler yani. O geçti gitti.
Pressure retarded osmosis'e dayanan enerji sistemleri var. Duymuşsunuzdur belki.
Neydi?
Pressure retarded osmosis. Bu tuzlu sudan hani tatlı su yani ters ozmoz süreçlerine dayanan hani bu yüksek basınç elde etmeye dayanan enerji sistemleriyle ilgili çalışma yapılıyor bildiğim kadarıyla. Onunla ilgili ne düşünüyorsunuz? Gördünüz mü?
Ya bilmiyorum ama mesela bak bu Direct Air Capture'dan kullanırken electrochemical, ona fazla girmedim. Onda kullanılan sistem elektrodialysis. Tamam mı? Yani çalışıyor ama büyük scale up'ı nasıl olacak bilmiyoruz. Çok fazla membrane lazım onun için. Tamam mı? Onları yapacak kapasitede şu anda yani dediğim gibi mesela ben carbon capture'dan veriyorum. Yani 1 milyon tonluk senede bir carbon capture düşünüyorsan yani sen hesap et kaç kilometre kare membrane lazım sana ve onun bir reliable supply'ı olması lazım. Devamlı gelecek çünkü onlar eskiyorlar, patlıyorlar, çatlıyorlar bilmem ne oluyor falan filan. Yani zor. Bunların scale up'ları zor. Bak bir sürü teknoloji, bak ben 30 senedir çalışıyorum. Bir sürü teknoloji geliştirmeye. Hiçbir yere gitmedi. Compressed Air Energy Storage. Ben çalıştım üzerinde. Dünyada hala 2 tane plant var. Biri Almanya'da, biri Amerika'da. Yok 30 senedir yapılmıyor. Integrated Gasification Combined Cycle. Belki 40-50 senedir var. Kemper örneğini verdim. Yeni yaptılar. 7 milyon dolara çıktı fatura. 2,5 milyar dolardan. Ve çalışmadı. Yok yani çalışan bir teknoloji yani son 30-40 senede sorarsan bana bir solar PV var. Fotovoltaik. Concentrated solar power bile fazla şey yapmadı. Bir de lithium ion battery. O da belli bir noktaya kadar. Yani bu teknolojilerin bir başladıktan sonra scale up olması çok uzun bir süreç. Yani böyle market ekonomilere bırakırsanız olmuyor. Çünkü financing yok. Hani şey olsa devlet gelecek aynı 2. Dünya Savaşı'nda olduğu gibi yani Amerika'nın yaptığı gibi. Tamam arkadaş yani biz bu işe giriyoruz al sana para. Yapılacak. Ya o zaman yaparsın belki yani 1, 2, 3, 5, 10 tane 20 tane yaptığın zaman o learning curve şey oluyor. Tekrarlanabilir oluyor. Öbür türlü financing yapamıyorsun. Şimdi bak bu camper hikayesi oldu. Bugün öldür Allah kimse integrated gasification'a $1 yatırım yapmaz. Yani zor. Yani ben başka yeni teknoloji bilmiyorum yani bunları o diğer işte bu elektrodiyalisis şunlar bunlar falan filan yani bunların belli bir seviyeye gelecek yani bir impact'i olacak imkansıza yakın. O yüzden elinde ne varsa onu kullanacaksın. Nükleer var elinde. Niye kullanmıyorsun? Yani bu korkuya gerek yok işte. Almanya gördü. Solar'la wind akıllı olarak yapılırsa onlar da yani şu anda mature teknolojiler kullanılması lazım. İşte energy storage, battery gittiği yere kadar ondan sonra compressed air energy storage mesela yapılabilir. Ama pahalı. İşte pumped hydro onu kullanacaksın mümkün mertebe. Yani böyle. Carbon capture'da yani carbon capture dediğim gibi yani bir şeye çözüm olmaz tek başına yani rakamlar ortada. Ama yani belli yerlerde kullanılırsa yani bir işe yarar. Ama dediğim gibi bir de o işin öbür tarafı var. Yani şimdi bu kadar popoyu yırtmaya da gerek var mı? Yani bazı yerlerde var, bazı yerlerde yok. Mesela yani Türkiye için şey olsam ben o kadar takılmam yani ona. En azından karbondioksite. Yani öbürleri çok kötü çünkü etrafı zehirliyor. NOx, SOx bilmem ne o partikülatlar adamı hasta ediyor, öldürüyor. CO2 tamam okey birikecek bilmem ne olacak işte şey şu kadar artacak işte 2060'ta bilmem ne olacak. Şimdi o kesin bir bilim değil. Hani o yöne gitmeyelim mümkünse okey ama onu yapmak için de kendimizi batırmayalım yani.
Tam da bu noktada ben başka bir konudan söz edecektim. Bu benim kişisel fikrim de kendi araştırmalarıma dayanan kişisel fikrim de karbondioksit oluşumunun söylendiği kadar bir an önce çözüm bulunması gereken bir konu olmadığı yönünde bir iklim küresel ısınma inkarcısı değilim ama çok fazla abartıldığı görüşündeyim.
Ya abartılıyor işte dedim yani inkara gerek yok. Şu Unsettled kitabını yani bulun ve okuyun yani adamın bazı argümanları var yani ona da yani körü körüne inanmayın ama yani iş öyle söylendiği gibi Allah bittik gidiyoruz yanıyoruz falan filan değil.
Değil. Sanıyorum bu belki de dünyada başından beri birkaç cycle'dan bir ısınma cycle'ın içerisinde de yaşayabiliyor olabiliriz.
belki insan etkisinin daha fazla olduğu bir cycle'da olabilir. Benim bu konuda çok kesin bir fikrim yok ama asıl söylemek istediğim şu: bu CO2'dan önce su kirleniyor. Material problemi var. Özellikle renewable enerjiyle beraber ve automation'la beraber bu rare earth elements, bunların dünyada bol olmalarına karşın dağınık olmaları ve dağınık olmalarından dolayı çıkarılması için harcanan para, manpower, kirletilen su, toprak, yerinden edilen insanlar, tarım alanlarının tarım alanlarının yiyecek oluşturma, yiyecek elde etme yerine bu işlerde kullanılması. Bunlar yeni yeni konuşulmaya başlandı ama çok da üzerinde sanıyorum ekonomik olarak bir yapısı kurulmadığı için fazla konuşulmuyor. Ama şu var, sanıyorum bu elektrikli araçlardan sonra ne diyorlar? Life Cycle Analysis of Material Footprint mi? Öyle bir kavram gelişti. Umarım o kavramın geleceği daha akıllıca bir şekilde devam eder.
İşte bu geçen haftaki konferansta biri onu şey yaptı, yani bir numaraları şey yaptı. İşte elektrik vehicle'lar şu sayıya ulaşırsa şu kadar bilmem ne gerekecek falan filan diye. Yani rakamlar tabii astronomik. Yani bilmiyorum ama dediğim gibi yani bir de çok para dönüyor tabii bu işlerde, yani research olsun bilmem ne olsun.
Şimdi bu sorunun literatürde yeri var mıdır ya da feasible mıdır bilmiyorum. Aslında öğrenmek istediğim de o biraz. Az önce hocamız da sordu. İşte kömür bir seçenektir, tamam, ya da doğalgaz da bir seçenektir ama işte dışarıya bağlıyız. Kömürde biraz daha iç kaynaklarımıza bağlıyız. Hibrit bir cycle söz konusu olamaz mı burada? Yani asıl odak noktam evet doğalgaz ama herhangi bir kriz anında da kendi iç kaynaklarıma yönelebileceğimi biliyorum. Dışarıya olan bağımlılığımı azaltmayı hedefliyorum. Kendime yetmeyi hedefliyorum aslında. Burada filtrasyonu da dert etmeyeceğim çünkü asıl odağım kömür kullanımı da değil. Yani power plant her iki ihtiyaca birden cevap verebilir mi?
Yani bilmiyorum, yani tam anlayamadım ama yani nasıl bir hibrit?
Yani kimi zaman kömüre yöneleceğim. Diyelim bir projeksiyonda, uzun bir projeksiyonda 2 sene kömür yakacağım ya da herhangi